Yes, sir.
Right. Okay. So in the previous class, we were discussing variable length compression, variable length lossless compression. And here's a block diagram of the problem. We're given a source file or an input file of size n, and the goal is to construct the encoder and the decoder f and g, or the compressor and the decompressor f and g, so as to minimize the expected length or the average rate. So since we're dealing with variable length compression algorithms, we saw a number of requirements that a good variable length compression algorithm should satisfy. Firstly, we saw that it has to be non-singular if it has to be perfectly lossless. And then we saw two different conditions of increasing strictness. It could be uniquely decodable, but a more desirable condition is that the code be prefix-free or instantaneous. Right? And we saw some examples of codes which are non-singular but not uniquely decodable, which are uniquely decodable but not prefix-free, and an example of a code which is prefix-free. And towards the end, we were discussing an asymptotically optimal scheme in the sense of minimizing the rate and the way it works. So let me just very quickly go through what we saw. So the code word was split into two parts, a header and a sequence of compressed bits. The header has size roughly log n bits, and this sequence CS could depend is of variable length and depends on the actual sequence which needs to be compressed on the actual raw file. Right? And the way we assigned CS for each input sequence xn is that we sorted all the sequences in the order of decreasing probability, and then we assigned code words of increasing length for each of them. So x1n, the sequence with the highest probability, would get the empty code word that is nothing as the corresponding code word CS. For x2n, it is just the bit 0. For x3n, it is 1. For x4n, it is 0, 0, and so on. Right? So the actual compressed file would consist of two parts. So the length of CS in binary form, so that is the header, and then the sequence CS itself. Right? And as one of you pointed out, the length of CS, the length of CS of xn is basically equal to the floor of log I. So if xn is the sequence with the ith highest probability, then it has a corresponding sequence, code word sequence of length log I to base 2. Okay. So the actual compressed length is order log n plus log I to base 2. And then I made a claim saying that the probability of occurrence of xin is always greater than or equal to 1 over I. So if xn is the sequence with the ith highest probability, then the probability of the sequence is at least 1 over I. Can one of you justify this statement? Yes? Anyone? So x1 is the sequence with the highest probability, x2 is the sequence of second highest probability, x3 is the sequence of third highest probability. So the probability of xn is, sorry, so I made a slight mistake over here. So this should be less than or equal to 1 over I. So x1 is the sequence of ith highest probability, implies that the probability of xi is less than or equal to 1 over 1. If x2 is the sequence of second highest probability, then this has probability at most half. The probability of x3 is less than or equal to 1/3. probability of x4 is less than or equal to 1/4, and so on. Can one of you justify this? Can you say why this has to happen?
Sir, if it was greater than I 1 by I, then all the above I minus 1 probabilities will also be greater than 1 by I.
Correct.
That would
So
make the probability greater than 1.
exactly. So if the probability, so you can prove this via contradiction. So suppose that the probability of xi is strictly greater than 1 over I. Then the probability of x1, probability of x2, probability of xi minus 1 would all be greater than 1 over I. Because after all, xi is the sequence with the ith highest probability, right? So x1, x2, x3, and so on should have a higher probability than xi. And if this were the case, then if you sum over j going from 1 through I, so j equal to 1 through I, probability of xj, then this would be greater than I times 1 over I, which would be strictly greater than 1, which is impossible. Right? So this leads to a contradiction. Therefore, the probability of xi should always be less than or equal to 1 over I. And once we have this, just by rearranging these terms, we get that I should be less than or equal to 1 over p of xn. And so the expected value of k would be just, so if I plug this back in here, then the expected value of k would be order log n plus expected log 1 over p of xn, and which so this quantity, as we know, this is equal to the entropy of xn, and therefore the asymptotic rate would be equal to limit n tends to infinity of h of xn over n. Right? So this is indeed
So,
optimal. Yes, Ritwik.
so this way of proving proves that not all of them can be greater than 1 by I at the same time. It does not prove that one of them can be more and other can be less than 1 by I.
So it proves that for every I, the probability of xi should be less than or equal to 1 over I, right?
So we contradicted that for every I, not
Correct.
it cannot happen that the probability is greater than 1 by I for every I, but it can happen that so
No.
according to this way of proof, it can happen that so some of them are greater, some of them are less.
No, right? It is so remember that xi is the sequence with the ith highest probability. Correct? So
Yes,
if
sir.
so it cannot happen for any I, not just for some I, right? So if even if so so if even if there is one such I such that probability of xi is greater than 1 over I, then we get a contradiction, right? So let's take a separate page. Right? My claim is that so for all I, where I is between 1 and cardinality of x to the n, the claim is that the probability of xi to the n is less than or equal to 1 over I. Okay. So if this condition is not true for even a single I, then it leads to a contradiction, right? As we just saw.
So how can we prove for a single I? Let's say we take just one I. For one
Okay.
I, we take it is greater than 1 by I, and for all the other I's, we take it is less than 1 by I.
So that can't happen, right? So by definition, xi is the sequence with the ith highest probability, correct?
Yes, sir.
Right? So if xi is the sequence with the ith highest probability, And even if for one I this condition is not satisfied, so suppose that there is any one I which does not satisfy this. Okay, even a single I. So it means that for that particular I, probability of xin is strictly greater than 1 over I. I don't really care about what happens to the other i's. Okay, so maybe for say x10, it is strictly greater than 1 over 10. Okay, for 11, 12, and so on, I don't really care. I don't care if this is not satisfied for 9, 8, 7. Doesn't matter. There is some one I such that probability of xi is greater than 1 over I. Okay.
Yes, sir.
Okay. So if the probability of xin is greater than 1 over I, then it must be true that the probability of x1n is greater than 1 over I. Probability of x2n is greater than 1 over I. And so this is implied by the above statement, right?
Yes, sir.
Probability of xi minus 1 n is greater than 1 over I. Agreed?
Yes, sir.
Right? So this implies that summation j going from 1 through I of probability of xjn, this is strictly greater than 1. Correct?
Yes, sir, I get it.
Right? And therefore, this is a contradiction. All right? Okay, good. So, any other questions? All right. So we've already seen a scheme which achieves the entropy rate, right? So here we have a scheme. We know that at least asymptotically this is the best that we can do. In fact, this is close to the best that we can do for any n. If you sort of ignore the header part, then you can't really do any better than this particular assignment. But then there is one disadvantage of this particular scheme. Of course, firstly, you need to know the probability of xn, right? And also, the other disadvantage is that in order to implement the scheme, both the transmitter and or both the encoder and the decoder need to maintain this table of all possible sequences and all possible code words, and that is it's not efficient, right? Because for each n and each probability, you will need to reconstruct this entire table, which is clearly very wasteful. So our goal will be to design sort of more efficient compression algorithms, which of course minimize the expected length, the expected compression length, and are also sort of very easy to implement, easy to compress and to decompress. Okay. So here's another question. Now I just described the scheme. Is this scheme prefix free? Is it instantaneous? Yes. So I see some people saying no. Can you say why it is not instantaneous? So remember, so when I say that the scheme is instantaneous, the entire code word. So I'm not talking about just CS itself, but the concatenation of CH and CS, both the header and the sequence CS. When I concatenate them together, this gives me the code word. And so is this sequence of code words instantaneous or not? So clearly CS itself is not instantaneous. But what can you say about the concatenated code word CH and CS?
It is instantaneous.
It is instantaneous. Okay. Yes, it is in fact instantaneous. Because when you once you read CH, you know exactly how many bits of CS you need to read, and therefore you know exactly when to terminate. You don't really have to decode the next sequence in order to get you the first sequence XM. Right. So in fact, this code is instantaneous. So it's a prefix-free code which achieves a rate or which achieves a compression length bounded from above by order log n plus the entropy. Okay. So this is indeed this is optimal for large n, but what we are now going to do is we are going to see compression algorithms which work for any n. Even if n is very small, we still want to design prefix-free codes which achieve the best possible compression lengths.
Hello, sir.
Yes, sir.
CH then must be written in this binary form.
Yes. So the entire thing is binary sequence. So CH is going to be a binary string of length, whatever log n plus log cardinality of x.
Yes, in last class
Yes.
you wrote, for
Correct.
example, x4
Correct.
200.
Correct.
Uh, so it must
So
be written 1100.
yes. So the two will be. So for example, if I take, let's say that n is equal to whatever 16. Okay, so if I take n to be equal to 16, then log n will be uh, 4, right? So I would encode x to n as 0001. So this would be ch followed by 0, which would be cs. If I want to encode, say, x5n, then the cs corresponding to x5n, what would that be?
Zero one.
It would be 0, 1. So this is of length 2. So ch would be 0010, which is the binary representation of 2, followed by 0, 1. This would be my cs, and so on.
Okay, so then it will be prefix free.
Yeah, so this is prefix free, right? Any other questions? Okay, right. So we are still, so now the goal is to design efficient prefix-free compression algorithms, which minimize the expected length. So even before we start to design, we'll see some necessary and sufficient conditions for a particular code to be prefix-free. And this is given by what is called Krafts inequality. Which is a very powerful result that we'll use time and again. So it says, so Krafts inequality says that if we have, so for any prefix-free code, if the code has code word lengths L1, L2, L3 up to say LK, suppose that the alphabet or the number of possible inputs is K, and the corresponding code word lengths are X1, X, the corresponding code word lengths are L1, L2, L3 up to LK, then summation I going from 1 through K, 2 to the minus Li should be less than or equal to 1. Okay, so let's take an example. So can you give me an example of a prefix-free code for say 4 symbols? So we have A, B, C, and D. So can one of you give me an example of a prefix-free code?
So 0, 1, 0, 1, 1, 0, 1, 1, 1.
Okay, 0, 1, 0, 1, 1, 0, and 1, 1, 1. So this is a prefix-free code. All right, so what are the corresponding code word lengths in this case? Yes? So it's 1, 2, 3, and 3. Right? And what is, so this is L1, L2, L3, and L4. Right? So now what is this equal to? Summation I going from 1 through 4, 2 to the minus Li. So this is half plus 1 by 2 square plus 1 by 2 cube plus 1 by 2 cube. Right? What is this equal to? It's equal to 1. Right? So this term on the left is sometimes called the Krafts sum. Right? And this is a code which happens to satisfy Krafts inequality with equality. Okay, so this is one particular code, and we saw that it satisfies Krafts inequality. Now let's take an example of a code which is not prefix free. So let's take that example that we had. So we have A, B, C, and D, and it's 0, 1, 0, 0, and 0, 1. Okay, so in this case, what is the Krafts sum equal to? So it's equal to 1.5. right? So it's half plus 1/4 plus 1/4, and that is equal to 1.5. So it does not satisfy Krafts inequality. So any prefix-free code must necessarily satisfy Krafts inequality, right? But then it is possible that a prefix, so it's possible, it doesn't mean that every prefix-free, so every code which satisfies Krafts inequality must necessarily be a prefix-free code. So for example, for these same lengths, I can always construct a code which is not prefix-free. So for example, if I had 1, 1, 0, 1, 1, 0, and 1, 1, 1, this code still satisfies, the code word lengths still satisfy Krafts inequality, but then this code itself is not prefix-free, right? But although it doesn't mean that the code is prefix free, what it does imply is that if you have a sequence of code word lengths L1, L2 up to Lk which satisfy Krafts inequality, the following is true. We can construct a code with these lengths and is prefix free. Okay, so as long as you give me a sequence of lengths L1, L2, L3 up to Lk which satisfies Krafts inequality, I can construct a code with the corresponding code word lengths and it is also prefix free. So for example, let us say that we have the code word lengths 1, let's take say 2, 2, 3, 3, 3. So does this satisfy Krafts equality? Oh, sorry, Krafts inequality? Yeah, so it does satisfy Krafts inequality, right? Because so what is the Kraft sum equal to? So it is 7/8, which is less than 1. And here is one code which is prefix free. So I can take 0, 0, 0, 1, say 1, 0, 0, 1, 0, 1, and 1, 1, 0. So is this code prefix free? It is, right? So it's prefix free and it has the same lengths, the code word lengths as I specified over here, 2, 2, 3, 3, 3, and it is prefix free. Okay, so now let's try to prove these two statements. That is, any prefix-free code must necessarily satisfy the Krafts inequality, and given any sequence of lengths which satisfy Krafts inequality, we want to be able to construct a code with the corresponding lengths and is also prefix-free. Okay. So any questions until now? All right. So in proving Krafts inequality, we'll prove a very nice property of any prefix-free code. Okay. So in fact, we'll look at a different. So we'll see a different way of looking at binary codes in general. Right. So suppose that I have some code. Let's say 0 0. Let's take the example that I have over here. 0 0 0 1 1 0 0 1 0 1 1 1 0. Now, given any such sequence of binary strings, I can put these strings as vertices in a tree, in a binary tree. So let's look at. So suppose that I have a sequence of strings of maximum length L max. Okay. What I'm going to do is I will construct a binary tree of depth L max. Okay, or height L max. So in this case, it is 3. So the height of this tree is 3. And I'm going to label each edge in this tree with 0 or 1. So the left edge will be 0, the right edge will be 1. Okay, so now each code word corresponds to one particular vertex in this tree. So I have A, B, C, D, E with corresponding code words 0 0 0 1 1 0 0 1 0 1 and 1 1 0. So A would be this particular vertex over here. So 0 1 would be B, which is this particular vertex, and then 1 0 0 would be this vertex over here. 1 0 1 would be this particular vertex over here, and 1 1 0 would be this particular vertex over here. Okay. So this is one way to sort of represent a binary code or any set of code words on a binary tree of height L max. Okay, so each of these vertices corresponds to a particular code word. All right. So now let's look at the other example. So this one. So 0 1 0 0 0 1. So the maximum length is 2. Maximum code word length is 2. I have 0 1 0 0 and whatever 1 1. Let's say. This is A, B, C, D. Okay, so I have 0, which is A, 1, which is B, 0 0, which is C, and 1 1, which is D. Okay. Now, is there something that you can observe between these two? So is there a difference between these two? Is there something that you can notice here?
On the same level of the tree, we cannot have edges on both the sides, I guess.
On the same level, sorry, I didn't get what you mean.
I mean, like as we can see in the above graph, A and
Okay,
B both lie on the same side, and on the
okay,
other side, we do not have anything. And when we go to the
okay,
next level, we see C, D, E on one side, and others, there aren't any others on the other end.
okay. Well, okay, so maybe we need to put it in a slightly different manner. I see something in the chat also. So one thing that you notice is that for the second example, for this particular example, the code word corresponding to some particular sequence lies in the path of the code word corresponding to some other particular sequence. So if you start from the root, so this is, so given a tree, this is called the root, and the last, so this is the root, and the ones at the very bottom are called the leaves. Okay, so anything which lies above is called a parent. So for example, this is a parent of this, and correspondingly, this is a child of this, right? So in this particular example, you've seen that one of the code words is a parent of some other code word. Or if you go from the root to a particular code word, then there is another code word which lies along that particular path. Whereas in the first example, no code word is a parent or an ancestor of which, by an ancestor I mean a parent of a parent or a parent or a parent of a parent of a parent and so on. So no code word is an ancestor of any other code word, right? So whereas in the second example, we see that there is at least one code word which is an ancestor of some other code word. Okay. So here's a question. If I have a prefix-free code, then is it possible that one code word is an ancestor of another code word?
No.
No, right? And that basically just follows from definition. So prefix freeness So if I have a prefix-free code, then the corresponding tree representation of that code has the following property, that no code word is an ancestor of any other code word. And that is easily seen from the tree, because any ancestor, so if you take any particular vertex along this tree, then, so for example, if I take this particular vertex, then the code words which lie along this path, along this particular path, these are all prefixes of this particular code word, right? So if I take 000, then the code words along this path are 0 or 00, and both of them are proper prefixes of this particular code word. And since the code is prefix free, no code word can be the ancestor of any other code word. Okay, so that's a very nice property that prefix-free codes satisfy. So let's use this particular property. So now we've seen that if I construct the tree of depth Lmax, then all these trees have to satisfy. Then for any prefix-free code, no code word is an ancestor of any other code word. Okay. So if I have a tree of depth Lmax, then what is the number of leaves that are possible? So if I have a binary tree of depth L max, then how many leaves does it have? It's 2 to the L max, right? Okay, that's great. So now let us look at all possible code words. Okay, so let's take any code word over here. So take this particular code word. So the code word has length, say li. Okay, take any code word of length li. Okay, and now look at the subtree, which corresponds to the entire subtree which is below the code word. Okay, so all of these code words. So how many leaves are there in the subtree starting from li? Correct. So it is 2 to the L max minus Li. And why is that? Because if I look at the subtree starting from the Lith level, then this is a complete binary tree of depth L max minus Li, and therefore this subtree would have 2 to the L max minus Li number of leaves. Okay, so that's fine. Now, if you look at any two code words, okay, take this code word, take any other code, take this code word and this code word, then can the subtrees below these intersect? So is it possible that the subtree corresponding to this has an intersection with the subtree corresponding? So if I have, so this is subtree 1 and this is subtree 2. So this is subtree 2 and this is subtree 1. Can the two subtrees intersect? No, right? Because it's prefix free, therefore no code word is an ancestor of any other code word. And if the two had to intersect, then it can only happen if one is an ancestor of the other. Right? So there is absolutely no possibility of an intersection. So therefore, the leaves on the ith subtree cannot intersect with the leaves of the jth subtree. This is good. So therefore, we know that the total number of leaves is 2 to the L max. And the number of leaves in the ith subtree is 2 to the L max minus Li, right? And no two subtrees can intersect, correct? So the total number of leaves must be at most the sum of the number of leaves on the ith subtree. So 2 to the L max minus Li, right? Now if I divide both sides by L max, I get that 1 is greater than or equal to summation I going from 1 through k of 2 to the minus Li, which is basically Krafts inequality, which I wanted to prove. Right? So just to do a quick recap, we saw that the only properties that we use were the following. So if I have the tree, the binary tree, the complete binary tree of depth L max, then it has 2 to the L max number of leaves. And if I take any code word of length Li, then the number of leaves in the subtree corresponding to this code word is 2 to the L max minus Li. No two subtrees can intersect with each other. So the total number of leaves is greater than or equal to the sum of the number of leaves in each subtree. And if I take the sum, then and I divide both sides by L max, I get Krafts inequality. Right? Any questions? Okay, so now suppose that we have so let's look at the other side of Krafts inequality. So suppose that I have a sequence of lengths L1, L2 up to Lk, which actually satisfies Krafts inequality. Okay, so these satisfy Krafts inequality. Okay. So my goal now is to construct a prefix-free code with these corresponding lengths. Any hints, any ideas what we could do?
So we can start with the parent node, and then from there we can draw the tree with length L1, L2, and so on Lk
So you want to construct different trees or just one tree?
in a single tree.
In a single tree, right? So I'll take L max to be the max of I of Li, and I'll construct a binary tree of depth L max. Okay, so I'll construct a tree of depth L max. I'll label these with 0, 1, 0, 1, 0, 1, and so on. And then, so I just have this particular sequence of lengths. Let's assume that this L1, L2, L3, and so on are in order of, say, increasing length. So L1 is less than or equal to L2, which is less than or equal to L3, and so on. So what I can do is I start from the root, I keep going to the left. Okay, so I go to the left and then I go up to depth L max. Every stage I'll go up to depth L max, and then at L1 I stop and I identify this as the first code word. So this is my code word C1. Now for L2, I'll keep going along the left, right? But at L2 minus 1, I'll fork. So maybe over here, I'll fork. Okay, and I'll identify this as this particular code word. So basically, once I choose a particular code word, then for the second code word, I can't choose anything which is along this path or which is below C1. But I can choose it in any other fashion I want. So for example, all of these are freely available to me. So in this manner, I'll keep going. I'll try to select something from the left, but if I can't, I'll just go to the right. So I'll keep going like this and so on. Right? And I know that this is possible because since it satisfies Krafts inequality, I should be able to select vertices such that no particular vertex is an ancestor of any other vertex, right? So this is indeed possible, and I would encourage you to just take a set of example lengths and try to construct these code words on your own by hand. So take a bunch of numbers, check whether it satisfies Krafts inequality, and then if it satisfies Krafts inequality, then draw this binary tree and then identify vertices on this tree which correspond to valid prefix-free code words. All right. So this lets us show the following. So we've seen that any prefix-free code must satisfy Krafts inequality. And if I have a set of code word lengths which satisfy Krafts inequality, then I can construct a code with these lengths. I can construct a prefix-free code with these lengths. But just because the lengths satisfy Krafts inequality doesn't necessarily mean that the code is prefix-free, because you can just have a bad example like the one I gave over here. So this satisfies Krafts inequality, but then it is not prefix free. But then you can make a small change, right? You can just replace this code word with a 0, and that becomes prefix free. Okay. Any questions? Okay. So Sheikh asks if the Kraft sum gives any measure about the optimality of the average code word length. So in fact, it doesn't. So it's a necessary and sufficient condition, but just because a particular code satisfies Kraft's inequality doesn't mean that it is optimal in terms of the average code word length. So for example, if I have if I have three sequences, x1, x2, x3, let's see. So clearly 3, 4, 4. So this set of code word lengths satisfies Kraft's inequality. But you can see that this is in some sense suboptimal, because you can actually construct a code of shorter code word lengths.
So,
yes, Sajid.
so can we say when the equality holds, the optimality is guaranteed for the lens, for the set of lens?
For the set of lengths,
When equality holds.
so okay, so indeed it does satisfy a certain form of optimality, but it doesn't necessarily correspond to optimality in terms of the expected length. And let me just explain why that is the case. So for example, let us take the code word lengths 1, 2, and 2. Okay, so this is a code. Okay, so it has code word lengths 1, 2, 2. This satisfies Kraft's inequality with equality, right? But then if you, sorry, but this is a statement only about the set of code word lengths, right? If in addition you also use the property that code words, that is sequences with higher probability get shorter code word lengths, then it is indeed optimal. But then you can always sort of do this assignment in a bad way. So let us say that the probability, so if I have three symbols, A, B, and C, with probabilities, say 1/3, 1/3 is bad. So 3/4, 1/4, and 1/4. Okay, so this is not good. Half, 1/4, and 1/4. Let's say as an example. Now, if I select A, B, C, if this is the assignment, then it's good. It does indeed turn out to be optimal. But Kraft's inequality in itself is insufficient, because if I label this as B, A, C, then the expected code word length is larger.
Yes, sir. So we can say that there exists at least one mapping from the lens to the symbols that will,
Yes.
give the optimal solution.
Indeed, yes. And that is what we will see when we do Huffman codes.
Okay, sir. Thank you.
Okay. All right. So let's very quickly do a quiz now. I'll put up the link in the chat box. All right, it is in the chat box. In case you're not able to access it, just let me know. We can take maybe 1 more minute. If you're done, you can leave. So non-singular doesn't, so it's non-singular not necessary for extensions. So if it's non-singular also for every extension, then it is uniquely decodable, right? Right. Is there anyone who hasn't submitted their quiz yet? Okay, so if there's no one, then I'll stop accepting responses. All right, any questions regarding what we've covered in class?
So these recorded lectures and slides will be posted in the Google Classroom.
So all of this is on. I haven't put up the notes yet, but the lectures will be, everything will be available in Piazza. So just go to the course description page, and I'll put links to all of these.
Sure, sir. Thank you.
Okay, so if there are no other questions, then I'll end the class.